So measurement error. So let's define what is a measurement, because this class is all about the measurements, right? So then measurement is an observation that made to determine unknown quantity. So we measure some quantity. Okay. And this slide looks weird. The thing is, we have two types of measurement. The first type of measurement is direct measurement. And second type of measurement is indirect measurement. By the way, I already posted this slide on module, so then you can download. So my version would be slightly different from yours, but you can download it and watch. So then direct measurement, as you can see in the picture, there are two people and they actually measure the distance directly using tape measure, right? So it can be measured with distance and angles, elevation difference, and so on. Indirect measurements is, we still determine the quantity, but using direct or another indirect measures. So, for example, the indirect measure is a quantity computed from the direct or indirect observation. So here the keyword is computed. So instead of measure directly, we compute. So in this case, to measure this tree height, we use a trigonometry, right? By measuring the angle, and we compute this height. Another example would be like a volume. So the way that we determine the volume of this cube is we measure the three different sides of the cube, and then we compute the volume. So this is an indirect measure. Characteristics of measurements. The first thing is, when you do the measurements, there is no measurement exact. It always has an error. So in a land surveying project, how to deal with the error is very important. So it has an error, and both true value of the observation and associated exact errors are never known. That is actually the dilemma that we have. So true value and exact error, if we know either of this, then we can find the exact value, but problem is we don't know it. We don't know them. So when you do the measurements, and very important technique that we have to learn is how to minimize or how to find the most probable number, right? So that is the key. So some examples of measurements, I listed here 3 of them. So scale division size. So then if you have like a analog scale, and there is a the scales, the division size, but if your arrow shows the middle of that, and then you need to guess, right? So then that is one example of an error. Miscentering of the instrument and the target. For example, when you do the leveling, and then you will actually read the rod, right? And then there is a division, right? And then you can actually have an error. Change of temperature is another example. So when you do the horizontal distance measure, then your measurement could be different when you do the summer or winter, right? So that is the some examples of error. So let's define what is an error. So error is a difference of the observed or measured value and its true value. So error is E is equal to X. X is observed or measured value. This is what you have, right? Minus X bar, which is a true value. Problem is, again, we don't know what is the true value. Or since we don't know what is the true value, so then we don't know what is exact quantity of error. So our goal is to find what is the most probable value or number close to the true value, right? So we will talk about this later. There are three sources of errors. The first one is natural errors. The natural error is a change of the atmospheric conditions in the environment. So that is, for example, the wind or temperature or humidity that actually affects your measurements, and then that is called a natural error. So I listed two examples here. The steel tape length changes with the change of temperature. Leveling observation is affected by the Earth curvature, right? If you have a very large land surveying project, and this could be a source of error. Second source of error is the instrumental error. So I showed you different, equipment, and instrument always has a, its internal, error. Okay, so then that's imperfection in the construction or adjustment of the instruments. So of course, if you pay more money, then you will have a more precise, the instruments. So knowing the instrumental error range is very important. Okay. So so those examples include the unevenly spaced scale graduation and the sensitivity of the level vials. Third source of error, this is in fact that we will actually focus, is personal error. So that is caused mainly by the limitation of human senses of the sight and touch. So the example is ability to read the graduation on the rod or tape, or rod is held slightly out of plumb. Okay, so then when we measure it, we use our sense. So then it always, could be a source of an error. Do you have any questions so far? Okay, then I want to point out that the difference between the the error and mistake. Okay, mistake is not an error. that is caused by the observer blunder, confusion, or fatigue, or poor judgment, and so on. So then this is not an error. And when you have a mistake, it could be a large random error, okay? So example, actual measurement was 79.36, but when you write on the field book, you could actually write 73.96 by mistake, right? So this is not an error. And record clockwise angle instead of counterclockwise. So then when you have this kind of mistake, then you will have a very large error, right? So why we differentiate the mistake from the error? Because error, we can deal with the errors with the statistical method, but mistake, we cannot. So that is the main difference, main reason why we differentiate the mistake from the error. There are two types of an error. The first one is a systematic. Second is a random. So let's first talk about the systematic error. So systematic error is also called a bias. So as you can see, we have a two probability function here, right, curve. And let's say that this is an actual or true error curve, or measurement curve. But when we measure it, and then we have this dashed line. So what you can see in the systematic error is the shape of the curve doesn't change, which means that underlying statistical characteristic doesn't change, but only the center line is shifted. So this kind of error we can easily fix by subtracting the bias, right? And move this dashed line to the along with this solid line, right? Second type of error is random error. This is sometimes called a compensating or accidental error. So in many cases, this is beyond the control of the surveyor, because we have, for example, in this case, I'm comparing two different cases. So we have a sharper curve or wider curve. So which one is more precise? Solid one or dashed one? Narrower curve is always, we have a more precise measurement, okay? So for example, then you can think about two types of instruments. So then you have theodolite 1 and 2, and one is a more precise, which means that we have the solid line for the one, and then if we have a more error, then it becomes a wider instrument. That is something that we don't have any control, right, for the given instrument. And when we have this kind of random error, then we will follow the law of probability. This is why we have to learn the probability or statistical technique. Precision and accuracy many cases we use this terms, mixed, but it has clear differences. So precision is a degree of the consistency between the observation, and accuracy is the absolute nearness to the true value of the quantity. So precision is something about the consistency, and then accuracy is about how close your measurement to the true value, right? So I have 3 cases here. So we have an actual measurement shown as a dot. So this is a grouped, right? This is grouped, which is showing that we have a consistency, high consistency. But this measurement is away from the center of the circle, which means that we have inaccurate measurement. And we just learned that 2 types of error. Do you remember what were those 2 types of error? Systematic and random, right? Yes, systematic and random. And when you have this kind of error or measurement, is this a systematic error or a random error?
Systematic.
Systematic, right? So when you have this kind of observation, then by subtracting the bias, so then you can bring this measurement to the center. Let's take a look at the second case. So the observations are not grouped, nor it is not close to the center. So this is neither precise nor accurate, right? So this case, when you have a random error, is this something close to the solid line or something close to the dashed line? Dashed line, right? So when you have this kind of error, unlike this one we can fix, right, this observation by subtracting the bias. But when you have this kind of error, there's not much things you can do, right? And third case is it is grouped and also centered, so both precise and accurate. And when I define the error is observation minus true value, right? But problem is we don't know what is the true value. So we need to guess what is a true value. But when we do the guessing, we want to make a good guess, okay? So although we don't know the true value, what is the best way to determine the quantity close to the true quantity? We already know, which is find the average, right? So more precisely, it is called sample mean, okay? Sample mean is, so when you say mean or average, that is mathematical, that means a true value, true quantity. But sample mean is can be calculated from this equation. So then that is not true value, but most probable value using the given data or given measurements. Okay, so you're all familiar with how to calculate the sample mean, right? So summation of M here is a measurement. So in this case, how many measurements do we have in the equation? How many measurements do we have?
N measurements?
Yes, small n, right? So this is a number of measurements, right? So then, and we call it, this is M bar. Again, this is different from true value, but this is, most probable value, okay? And another quantity we're going to use in the calculation is the residual. Residual is defined in the textbook. V is equal to M bar minus MI. M bar is again the sample mean, and MI is the measurement of ith trial. Okay. But if you recall that the definition of E was what? Error was equal to X, which is a measurement, minus X bar, right? X bar was true value. So we're going to use M bar as the true value. So then textbook use this term, but it is not consistent with our definition. So actually, the residual can be calculated MI, which is the current measurement, minus MN. M bar is what? This, the sample mean. And now I'm going to show you some, actual example how we can, use this statistical technique with the measurements. And the example is something related to the, theodolite. So I will first explain what are the theodolite, and then also what is a total station. So theodolite, I explained earlier, it is a optical equipment to measure angle, right? But the limitation of theodolite is it only measures the angle. It cannot measure the distance. So to do this, both work done, we use a total station. How many of you have heard about a total station? So total station is very popular in land surveying project. So total station consists of this theodolite and this pole, okay? And then the angle is measured with the theodolite, with this optical device, but it is also integrated with the electronic distance measurements. So it is called EDM. So then it has a laser. So then it has a laser distance equipment. So then you can actually measure the distance at the same time that you measure the angle. In our lab, we don't have a total station. We only have a theodolite. Okay. Okay, so this is angle observation from the precise total station instruments. So it has a 3-column table. It is a 3-column table. This table is from our textbook. So the first column is observed value. So using the total station, we can measure the angle, right? Is it clear? Can you see the screen back there? Okay. So this is the angle. And second column is number of observation. Okay. So if you see this, and then first thing you can notice is, we actually summarize in this table. We summarize a number from smallest angle to the largest angle, right? So this is in the order. And our first job is to calculate the sample mean. So how we can do that? Because first we take a summation of observed value, and then if you add all the number of observation, it becomes 100. So how we can calculate the sample mean? This summation divided by number of observation, right? So that gives you the sample mean. So sample mean can be calculated like this. And then most probable value of the observed angle is this: 27 degree, 43 minute, 24.9 second. So this is how we can find the most probable value as a sample mean. And once you know the sample mean, then you can calculate the residual, right? How you can calculate the residual? Definition of residual is your observation minus sample mean, right? But in the textbook, as I said earlier, the textbook author actually flipped this. So then sample mean minus MI to be consistent with the the textbook table. Then V for the first one, right? 5.4 is our sample mean minus this observation.
Why? I have a question.
Yes.
Why are we using that observation and not any of the other ones? Like why that 7 and 43?
Oh, why we only have this the residual of this observation only? Is that what you're asking?
It's like, why use the 2743 19.5 instead of 22.1?
Oh, this is one example, but we can actually calculate the the residual for all observation. So this is just one example. Did I answer your question?
Yes, and like in labs, you're gonna specify what residual we want, right? Like
so then the residual, residual can be calculated for the all observation value, and then that will be done when you calculate the when you determine the error boundary. I will show you later. In the class, do you have some questions so far?
I have one, if that's okay.
Yeah, go ahead.
So I get the mean that it's going to be 24.9, but where are we getting the most probable value from?
Oh, the other value is from this first part. So then for the simplicity, the table doesn't show the degree and minutes. Make sense?
No.
So
Are you asking for the 100?
yes. So then if you see the first value, do you see my cursor?
Yeah.
So then this is 27 degree 43 minutes, and the rest is the difference, right? So then up to the minute, all the the observed value is the same. Okay. So then for the simplicity, they just omit the first two values.
Okay.
Okay, then we can calculate the residual for the first one, and also there is another the quantity called the dispersion. So dispersion is showing the boundary of your data. Okay, so dispersion can be calculated the largest observed value minus smallest observed value. So in this case, 30.8 is the largest observed value, right? And the smallest one is a 19.5. So then the dispersion is 11.3. So if you have a larger dispersion, that means the smallest, the difference between the largest and smallest observed value is larger, right? And in general, you want to have a smaller dispersion, right? Because that will determine the width of distribution, right? And this is a way that you summarize your data in the table, but many cases you want to show this as a graphical form, right? So to summarize this data in the graphical form, what kind of diagram you want to draw?
Line graph.
Say it again.
It's a line graph.
Line graph, or have you, I think you are familiar with the histogram. You heard about that histogram? So histogram is a graphical representation of this table data. So to draw the histogram, the first thing you need to do is you need to determine the bin size or number of bins, right? So there are two different methods to determine the bin size or the number of bins. So the first method is to determine the class interval. So we can, in this case, in this example, we set the class interval is a 0.7 second, and you can see that the bin interval of the first bin is what from the -7.5 to minus 5.95 to minus 5.25, right? Which is the interval is 0.7 seconds, right? So then you can have this bin for the larger values, and then you can count how many observation is fall into that bin. So if you sum them up, then that would be 100 observation. So the first method is using the class interval. Second method is using the Sturgis rule. This is not a rule that you always to follow. So this is sort of the rule of thumb, but this is some good value to start with. Okay. So Sturgis rule is a rule for determining the number of bins to use in the histogram. And in the Sturgis rule, then k is equal to 1 plus 3.322 log base 10 n. So here the k is a number of beans in your histogram, and n is the size of data set. So in our, the total station angle data, if you apply the Sturgis rule, then k is equal to 1 plus 3.322 log base 10, 100, because n was 100, right? Then log base 10, 100 is 2, right? So then you will have a 7.644. So that means, according to Sturgis rule, you want to have the number of bean 7.644. But this is a number of a bean, so then you want to have a whole number. So you want to round up. So then you want to have like 8 beans, right? So when we use class interval of a 0.7 in our previous slide, then how many beans we had? If you use the first method, class interval of 0.7 second, you can count these beans, right? So then if you count that, I know that students are counting, so I will wait. So how many beans we have with the class interval of 0.7 second? We have 17 beans. If you count this, rows, it will be 17 beans. So question is, which number we have to use, right? So Sturgis rule is not mandatory to follow, okay? So then this is a good number to start with. So then you want to have this number or larger or smaller. So then main key point is I can show you in this slide. So this slide shows a histogram using the class interval of 0.7 second. So if you count these beans, then we have like a 17 beans, okay? And histogram, the x-axis is the size of residual, okay? Then y-axis is a frequency, right? And at the top middle point of the bar, you can draw the straight line connecting those points, and you can get the frequency polygon, right? And what you're seeing as a solid line is distribution curve, but this is a normal distribution curve. So depending on how you set the number of beans, this frequency polygon could look like normal distribution, or if you have a very small, for example, if you have like a 3 beans, then you will have a difference to the normal distribution, right? So the setting the number of bean is a more like a sort of trial and error, okay? But Sturgis rules to show you what is a good value to start with. Make sense? So I explained that the two quantities to assess the precision and accuracy. The first one was sample mean. Second was the residual. And I have two more to introduce. The third one is standard deviation. And the fourth one is variance. So standard deviation is interpreted as precision. Okay. Again, the precision is something related to the consistency or repeatability, right? So precision measures the precision. Standard deviation measures precision. So again, I know that you already learned this in your high school class. So sigma is a symbol for the standard deviation. Is equal to plus minus square root of VI squared. What was the V? V was residual, right? Divide by n minus 1. And variance is square of standard deviation. So by having this standard deviation, you can quantify the precision of your measurement. So this slide shows the mathematical definition of standard deviation, but the next slide I want to show you what is a standard deviation in graphical form. So when you have this normal distribution, and there is a point have like a slope changes. So this is called the inflection point. Okay, so then we have a narrower distribution, wider distribution. So then we have inflection points. So the standard deviation in graphic form, this is a distance to the inflection point to the center of this distribution, which is mean, right, or average. So, graphically, your standard deviation can be determined if you find the inflection point and draw the vertical line, and then this distance is standard deviation. And we have two cases, which is the bottom one, top one is narrower, the bottom one is wider, right? So then which standard deviation is larger, top or bottom? Bottom. Bottom is larger, right? So then larger standard deviation means you have further away from the mean, or you have less consistency in the measurement. So you can think that you measure the this desk length, right? But you measured 100 times, but student A measures and then come up with the first one, the top one, and then student B come up with the bottom one for the same table or desk. So then who has more consistency? The first one, right? So so then standard deviation is a measure of consistency or precision, okay? Do you have any questions so far? So when you have this, the sharper distribution, the area of this shaded region is the same. Okay, so then you will have when you have a the high precision measurements, then you will have the greater value in y-axis. Okay, then why we care about standard deviation? So back to our previous curve, I actually shaded in this x-axis is one standard deviation, right? So with respect to the center line average. So then if you measure this area, then this will be 68.27% of entire curve area. So that is defined as a one standard deviation. And this percentage of area percentage is same for the sharper one or the wider one, okay? Which means if you take 100 observation and roughly about 70% of your measurement will fall into this shaded area, no matter this is sharper or wider. And this is very important because this determines the requirements of precision of each surveying measurement, right? So standard deviation used to determine the tolerance of precision in your measurement. So if you have a one standard deviation, so then you can say, when you have a land surveying project, and your requirement is, one standard deviation, which means that if you take 100 measurements, then 70% should be, fit into that range. Okay, so that is the accuracy requirement, precision requirement. And this chart shows x-axis is 0.5 standard deviation, 1 standard deviation, 1.5, 2, 2.5, 3, and 3.5 standard deviation, okay? And then y-axis shows that percentage of area. So if you have 1 standard deviation, you have a 68.27, close to 70% accuracy or precision. If you have a 2 standard deviation, you end up with a 95% precision. And if you have a 3 standard deviation, this will be what? 99%, 7, close to 100, right? So have you heard about 6 sigma? Or okay, that is a very popular term of the consistency in manufacturing industry. So then if you have like a 3 sigma or 3 standard deviation, this is about 99.7, right? So that means if you produce like 1,000 the product, okay? If you manufacture 1,000 product, then the product with a defect will be 3, right? That is 3 sigma. But if you have a 6 sigma, then there will be very, very small value. So this is how they use, they control their quality, okay? So standard deviation is used for that. If you look at the 50% error, so then if you're the landscaping or like a land surveying project allows a 50% error, then that would be what, 0.6745 sigma, or many cases we require 95% error, which is a 2 sigma.